Welcome to homework.
The WMAP satellite launched in 2001, and it studied the cosmic microwave background radiation and was able to chart small fluctuations in the temperature of different regions of the background radiation. These fluctuations in temperature correspond to regions of large and small density in the early universe. The satellite was able to measure differences in temperature 2 times 10 to the negative fifth Kelvin at a temperature of 2.7250 Kelvin. At the peak wavelength, what is the difference in the radiation intensity per unit wavelength interval between the hot and cold regions? Okay, so to start this off, the radiation per unit wavelength is I of lambda. So we're going to use Wien's displacement law to find lambda max, 2.898 10 to the negative third meters times Kelvin over the temperature, which is 2.7250 Kelvin. We get 1.0634 times 10 to the negative 3 meters. So we need to find, to make our calculations a little bit easier, HC over lambda KT, which is 4.9659. And so E to the HC over lambda KT is equal to 143.44. So the intensity at this wavelength is equal to 2 pi hc squared over lambda to the fifth, 1 over E to the hc over lambda kt minus 1. Plugging in all of our values, and we get 1.9306 10 to the negative thirds watts per meter cubed. So the change in intensity, that corresponds to a small temperature difference. Delta I is equal to Ti over dt delta T, which is equal to the equation we had before. So 2 pi hc squared over lambda to the fifth, and then E to the hc over lambda kt over E to the hc over lambda kt minus 1 squared, hc over lambda kt squared delta T. This is equal to R of lambda times this bit. So plugging in values where our original that we found up here is R of lambda, and we get delta I is equal to 7.1 10 to the negative 8 watts per meter cubed. So measuring the tiny difference in the radiation intensity is like trying to tell the difference between a 60-watt bulb and a 100-watt bulb from a distance of about 4 miles. So not noticeable.